Let us begin slowly and without any sense of urgency. We are going to talk about sign measures, about absolute continuity and singularity, and about the Radon-Nikodym theory that ties these ideas together. All of these concepts lie comfortably inside measure theory, and they are best understood not as isolated definitions, but as parts of a single, coherent picture. It is helpful to think of this picture as a way of understanding how different notions of size, mass, or accumulation compare to one another. We will move gently. Ideas will return more than once. Nothing here needs to be grasped all at once. Motivation, why sign measures exist. Let us begin with a question that is both simple and surprisingly deep. Why would we want a measure that is allowed to take negative values? Ordinary measures, as you know, are non-negative. They assign size, volume, or mass, and these quantities are never negative. This restriction is natural, and in many situations it is exactly what we want. Length, area, probability, and mass all fit comfortably into this framework. But as analysis develops, we encounter situations where contributions naturally come with signs. We may want to describe the difference between two distributions of mass. We may want to keep track of gains and losses, excesses and deficits, or positive and negative charges. In probability and statistics, we often subtract one measure from another to compare models or expectations. In functional analysis, linearity becomes essential, and linear objects almost inevitably involve subtraction. In these situations, insisting that everything remain non-negative becomes restrictive. The structure of the theory pushes us toward a broader class of objects that still behave like measures, but allow both positive and negative contributions. This is where signed measures enter. It is important to emphasize that signed measures do not replace ordinary measures. Instead, they extend them. Every non-negative measure is automatically a sign measure. Nothing is lost. Rather, the theory becomes more flexible, more expressive, and more aligned with the linear nature of modern analysis. You can think of sign measures as a careful, disciplined way of allowing subtraction while preserving as much of the familiar structure of measure theory as possible. Let us rest here for a moment. The motivation is not exotic. It is simply the desire to describe differences in a rigorous way. Sign measures as differences of measures. A very helpful way to think about a sign measure is as the difference of two non-negative measures. This idea is not merely an intuition, it is foundational. Imagine having one measure that represents positive contribution and another that represents negative contribution. The sign measure records what remains after subtracting the second from the first. In regions where the positive contribution dominates, the sign measure is positive. Where the negative contribution dominates, the sign measure is negative. This viewpoint immediately explains why cancellation becomes important. If a set carries both positive and negative mass, these contributions may partially or completely cancel each other. As a result, the sign measure of a set may be small even though substantial activity is occurring inside it. This observation leads naturally to a question. How do we measure the overall size of a sign measure if cancellation is allowed? The answer is to temporarily ignore cancellation. We separate the positive and negative contributions and measure their sizes independently. The resulting quantity is called the total variation. It represents the maximum amount of mass present, regardless of sign. It is helpful to think of total variation as measuring how much is happening rather than what survives after subtraction. This idea will return again, and it provides stability and control in the theory. Jordan decomposition. One of the most reassuring results in the theory of sign measures is that every sign measure can be cleanly decomposed into two parts, a positive part and a negative part. This is known as the Jordan decomposition. It tells us that even though a sign measure may appear complicated, it can always be understood as the difference of two non-negative measures that do not interfere with each other. What does this mean intuitively? It means that there is a canonical way to separate all positive contributions from all negative contributions. Once this separation is made, each part behaves exactly like an ordinary measure. The uniqueness of this decomposition is crucial. It tells us that the positive and negative parts are not arbitrary choices. They are intrinsic to the signed measure itself. No matter how we approach the problem, we will always recover the same decomposition. The total variation of the sign measure is then simply the sum of these two parts. Once again, we see how total variation restores order. It gives us a non-negative measure that fully captures the size of the sign measure without cancellation. It is helpful to pause and appreciate this point. Sign measures may allow negative values, but they are not chaotic. They admit a precise and stable internal structure. Hahn decomposition of the space closely related to the Jordan decomposition is another idea known as the Hahn decomposition. While the Jordan decomposition splits the measure, the Hahn decomposition splits the space itself. The idea is that we can divide the underlying space into two regions. On one region, the sign measure assigns only non-negative values to measurable subsets. On the other region, it assigns only non-positive values. This is a statement about the geometry of the space as seen through the measure. Certain regions are inherently positive, others inherently negative. Unlike the Jordan decomposition, the Hahn decomposition is not unique. There may be many ways to choose such regions, but the existence of at least one such decomposition is guaranteed. The connection between the two decompositions is deep. Once a Hahn decomposition is chosen, it naturally leads to the Jordan decomposition by restricting attention to the positive and negative regions. Conversely, the Jordan decomposition encodes the same information in measure-theoretic form. It is helpful to think again about what this tells us. Even when signs are involved, the theory allows us to separate positivity from negativity in a clean and meaningful way. Absolute continuity between measures. We now shift focus slightly from individual measures to relationships between measures. Absolute continuity is a way of expressing that one measure does not see anything that another measure considers negligible. If a set is invisible to the second measure, it is also invisible to the first. In more intuitive language, absolute continuity means that one measure is controlled by another. The second measure determines which sets are too small to matter, and the first measure respects that judgment. This concept is central because it formalizes the idea of one measure being derived from another by reweighting rather than relocation. Nothing new appears where the reference measure sees nothing. It is helpful to repeat this idea in different words. Absolute continuity means that the first measure cannot concentrate mass on sets that the second measure ignores. The structure of small sets is shared. This notion will soon lead us directly to densities and derivatives. Singular measures at the opposite extreme from absolute continuity lies singularity. Two measures are singular if they live on disjoint parts of the space. There is a region where the first measure is concentrated and the second assigns nothing, and another region where the roles are reversed. Geometrically, you can think of one measure being spread smoothly across a region, while another is concentrated on a thin or isolated subset. Probabilistically, this corresponds to fundamentally different sources of randomness. Singularity tells us that no amount of reweighting can transform one measure into the other. They are supported on different worlds within the same space. This idea complements absolute continuity. Together, they describe two extreme ways in which measures can relate to one another. Properties of absolute continuity and singularity. These relationships behave in a logical and reassuring way. Absolute continuity is preserved under restriction to smaller sets. Singularity remains intact when measures are scaled. These properties interact cleanly with decomposition results. Most importantly, absolute continuity and singularity can coexist within a single measure when compared to another. This observation prepares us for a major structural theorem. Lebesgue decomposition theorem. The Lebesgue decomposition theorem states that any measure can be split into two parts relative to another measure. One part is absolutely continuous. The other part is singular. This decomposition is unique, and it provides a complete description of how the two measures relate. Conceptually, this theorem separates smooth behavior from irregular behavior. The absolutely continuous part behaves like a density. The singular part captures concentration and irregularity. It is helpful to rest here. This theorem unifies many ideas we have already encountered. Radon-Nikodym theorem. Motivation. Once absolute continuity is present, it is natural to expect the existence of a density. If one measure sees nothing new beyond what another measure sees, then it is reasonable to believe that the first measure is obtained by weighting the second point by point. The Radon-Nikodym theorem confirms this intuition. It states that absolute continuity guarantees the existence of such a density, and that this density is unique in a precise sense. This result is central because it transforms abstract measure-theoretic relationships into concrete functions. Radon-Nikodym derivative. The Radon-Nikodym derivative is the function that describes how one measure accumulates relative to another. It tells us how much mass is assigned per unit of reference measure. Integration with respect to the original measure becomes integration of this density against the reference measure. This reduces questions about measures to questions about functions, which are often easier to handle. Once again, it is helpful to repeat the intuition. Absolute continuity means reweighting, and the Radon-Nikodym derivative is the weight. Integration with respect to signed measures. Integration with respect to signed measures becomes natural once decomposition is available. We integrate against the positive part and subtract the integral against the negative part. Linearity is preserved. Cancellation is handled cleanly. Nothing mysterious happens. Familiar properties carry over. Differentiation with respect to Lebesgue measure. Differentiating a measure with respect to Lebesgue measure means identifying its density when it exists. Absolutely continuous components admit such densities. Singular components do not. This distinction mirrors everything we have discussed so far. Singularity revisited through differentiation. Singularity manifests as the absence of a density. Mass concentrates where Lebesgue measure sees nothing. This reinforces earlier intuition and closes the conceptual circle. Closing reflection. Let us conclude slowly. Signed measures allow us to describe differences. Decompositions restore order. Absolute continuity and singularity describe relationships. The Radon-Nikodym theorem reveals hidden structure. Together, these ideas form a foundation for probability theory, stochastic processes, and modern analysis. They show us that even in the presence of cancellation, irregularity, and complexity, there is deep structure and clarity. You can rest in the thought that measure theory, though abstract, is remarkably gentle once its ideas are allowed to unfold at the natural pace.